In this video tutorial, I am going to discuss about amphoteric nature of amino acid. Along with this discussion, we will also discuss about the Zwitterions, as well as isoelectric pH. Isoelectric pH, that is known as PI. Okay, and we will also discuss that how to calculate isoelectric pH. So let's start our discussion with this word amphoteric. What does amphoteric mean? Amphoteric that means acid and base. So when any molecule which has potential to act as a both as an acid as well as a base, at that time we can call that compound as a amphoteric compound. So any molecule which has potential to act both as an acid and as a base. So such compound is known as amphoteric compound. So here amino acids are amphoteric compound. That means amino acid can act as an acid as well as base. So let's try to understand that how amino acid will show its amphoteric property. Okay. So if you consider any amino acid, we know that all the amino acid contain at least 2 ionizable group, right? So amino acids they contain at least 2 ionizable group. So at least 2 ionizable groups are there. Ionizable groups, right? So what are these 2 ionizable group? One is the carboxy group, and another is the amino group. So carboxy group, how it is ionizable? So we know that it is a COOH group, but depending on the pH of surrounding, it can undergo ionization like this COO minus plus H plus. Okay. Similarly, amino group, depending on the surrounding medium's pH, it can undergo ionization to this NH2 plus H plus. Okay. This ionization, it is at the equilibrium, and this equilibrium depends on the surrounding pH, right? So we can say that all the amino acid, they contain at least 2 ionizable group. And why this word at least? Because amino acid also contains side chain R, right? And this side chain, if they contain extra ionizable group, then there will be a more than 2 ionizable group, right? So all the amino acid, they have at least 2 ionizable groups. Now to understand better way, let's carry out one hypothetical experiment. Suppose in this beaker is filled up with the solution, and the pH of the solution is extremely low. So this is extremely low pH solution. That means hydrogen ion concentration is very high in this solution. So schematically, let's show these hydrogen ions as these red dots. Okay. So this solution is full of H plus ions as the pH is very low. Okay. Now in this case, if you put up amino acid over here, what will happen to this amino acid? See, it is full of hydrogen ion. So what will happen? All the ionizable group in this amino acid will get protonated. Why? Because there is so much concentration of protons. This H plus, that means proton. Okay. So due to high concentration of protons in this solution, the ionizable groups of this amino acid will get protonated. So what will be the scenario over here? The carboxy group in acidic condition, it will be in this COOH form, right? The COOH form is the protonated form of the carboxy group, right? And what about the amino group? Amino group will also be in the protonated form. So amino group will be in this form, NH3 plus form, right? Now let's create a reverse situation. In this beaker, again solution is filled up and this solution's pH is very, very high. It is extremely high pH. That means H plus concentration, or you can also call it as a proton concentration, is very, very low. Okay. So, if we show protons by this red dot, we will show only 2-3 dots, right. So, very less proton concentration is there. So, I had shown less red dots, and in this solution if you put up amino acid, what will happen? This solution's proton concentration is very low. So, the ionizable groups of amino acid, they will lose its proton. So, all the proton will be given to this solution. Why? Because solution's proton concentration is very low. So, whatever proton this amino acid will have, it will get lost into the solution. So, in alkaline condition, this carboxy group will be in the form of COO minus. This is the deprotonated form of the carboxy group. Amino group, it will be seen as a NH2 compound, right? NH2 group. Why? Because this is the deprotonated form of amino. One hydrogen is less. So, now as we can see that under different pH condition, carboxy group and amino groups protonated status is different, right? And if you look at this compound, you can see that these are the protonated group, right? Protonated group. And these are under alkaline condition, this carboxy and amino, they are seen as a deprotonated group, right. Now, as these are protonated, they can become a proton donor, right, proton donor. Why? Because they have proton. So, if situations are favorable, they can act as a proton donor. Whereas, in this case, the deprotonated, they do not have proton. So, here they can act like a proton acceptor, You can also call it as a H plus donor or H plus acceptor, right. So, as per the definition of the Bronsted definition of acid base, whenever some compound is proton donor, we call them as a acid, and whenever some compound is acting as a proton acceptor, it is known as base. And remember, this carboxy and amino both are part of amino acids, right. So, can we say that amino acid can act as an acid as well as base depending on the pH of the surrounding, right. So, this is matching with the definition of the amphoteric nature, right. So, that is why we call amino acid as a amphoteric compound. Now, let us try to understand this concept by taking example of the glycine. Okay. We know the structure of glycine amino acid, right. Glycine has a side chain as a simple hydrogen. Okay. So, now suppose this is the scale of pH, right. Here 0 pH and here maximum pH, that can be a 14. Now, if we draw the structure of glycine, on one side there is hydrogen, on another side there is side chain, and here the side chain is also H. On one side there is a carboxy group is there, and on another side there is amino group, right. Now, when this amino group will get deprotonated and when this carboxy group will get deprotonated, that is dependent on their pKa value. Okay. So, here the pKa value of the amino group is the 9.6, and the pKa value of the carboxy group, it is the 2.34. Okay. Now, what is the meaning of this pKa? This is pKa of amino and this is the pKa of carboxy group. The pKa of amino is 9.6, that means when pH is more than 9.6, this amino group will be deprotonated. Here the pK of 2.34 of carboxy group, that means when pH of the surrounding medium is more than this 2.34, at that time carboxy group will be deprotonated. Okay, so let us try to understand over here. So, this is 2.34, let us mark on this pH scale that this is the point where 2.34 pH occurs, and 9.6, lies somewhere over here. So 9.6. So this is the boundary, right? So now let's suppose that in this case here at this pH, if you put up amino acid solution, what will happen to its amino group and carboxy group? So here it is extremely low pH, right? So as we had seen in this case, what will happen? Both the group will be in the protonated form. So carboxy group will be in the form of COOH group, right? And amino group will be in the form of NH3 plus form. Why? Because both of these are protonated. And if you go on increasing the pH of solution, so in a sense you are titrating this solution. So as soon as this 2.34 mark is crossed, what will happen? More and more of this glycine, this COOH group, it will start losing its proton. So now COOH, that is carboxy group, will be in the form of COO minus. What about this NH3 plus? Will it lose its proton? No, it will in the form of NH3 plus. So here if you move into this direction, if you go on adding alkali to this solution, that means pH is increasing. What will happen? More and more COO will lose its proton, right? And NH3, it will not lose its proton. But as you cross this mark, this 9.6 mark, what will happen? More and more NH3 plus will also start losing its proton. So here we have carboxy group as a COO minus and NH3 plus group will be as a NH2. Why? Because beyond the 9.6 pH, this amino group will in the state of deprotonated form. So here you can see this is the extremely high pH, right? And at that place both the groups are deprotonated, which is matching with our this hypothetical experiment. Okay. So here you can see the charge, the net charge of the amino acid is changing. What is the net charge? Here the net charge of this carboxy group is 0 and NH3 group is plus 1. So net charge of amino acid is going to be plus 1. Here carboxy group carries minus 1 charge, amino group carries plus 1 charge. So net charge is 0. Here carboxy group carries minus 1 charge and amino group carries 0 charge. So net charge is going to be a minus 1, right? So this situation is interesting. See, here we cannot say that amino acid is uncharged. No, amino acid is charged. Why? Because it is negative charge on one end and positive charge at the other end. We can call this amino acid as a dipolar. Okay, here at this place amino acid is acting as a dipolar, and dipolar also the positive and negative both are in equal quantity, in equal amount. Okay, so whenever such scenario is there, that the amino acid carries both the charges in equal number, positive and negative. So what will happen? The net charge of this amino acid will become 0. At that time we can call particular amino acid as a Zwitterion. So what is the definition of this Zwitterion? The definition is that at a specific pH, see at this range, at this specific pH, the amino acid carries both the charge in equal number, right? Both the charge in equal number and exists as a dipolar ion, and which is known as Zwitterion. So at this point the net charge on it is 0. Okay, so let's write down the definition of Zwitterion. It is at a specific pH, because this is not, Zwitterion formation is not occurring at any pH, right? It is occurring at a specific pH. So at a specific pH, the amino acid carries both the charges in equal number. In case of glycine, it is minus 1 and plus 1, right? And exist as a dipolar ion. Why dipolar ion? Because on one pole it is negative charge and on another pole it is positive charge, okay, which is known as Zwitterion. Okay, and here at this pH the net charge is 0. You cannot call this molecule or Zwitter ion as a neutral ion? No. Why? Because it has some specific charge. Now, you can easily imagine that during this pH range, during this much pH range, we know that in this pH range, we will see the Zwitter ion of particular amino acid. Here the example is of the glycine, right. But at which specific pH this Zwitter ion will be the maximum? So, logic says that at exact midpoint of these two, suppose it is the midpoint of these two, at this specific pH, maximum of the amino acid will be in the Zwitter ion format. So, how to find out the exact midpoint of these two? So, we have to average out this 2.34 plus 9.6 divided by 2. So, whatever the answer of this, it will give the Pi of particular glycine, right, because we are considering pKa of the glycine values. So, what will be the answer of this? So, 11.94 divided by 2 and the answer will be 5.97. So, this is the isoelectric pH of the glycine. So, here what will be the definition of isoelectric pH? So, isoelectric pH. What is the definition of isoelectric pH? It is the pH at which molecule exists as a Zwitter ion or dipolar ion. So, let us write down the definition. Isoelectric pH is the pH at which molecule, and in our case it is the amino acid, it exists as a Zwitter ion. Zwitter ion, that is known as the isoelectric pH, and by this formula you can easily calculate what will be the Pi of this amino acid. Okay. Now, in case of glycine, everything was simple. Why? Because it carries only 2 ionizable group. Okay. Things will become complicated when there is a more than 2 ionizable group. So, let us take one example of glutamic acid, or you can also call it as a glutamate. So, if I draw the structure of glutamate, there is central carbon, one side there is hydrogen, here we have carboxylic acid group, here we have amino group, and there is a side chain, and here the side chain is CH2 COOH. So, here it has 2 carboxy group and 1 amino group. Now, we must know the pK value of all these 3 ionizable group. So, pK value of this COOH group, it is the 2.19. The pK value of this COOH group is 4.25, and the pK value of this NH3 plus, it is the 9.67. Okay. Now, how to calculate Pi? How to calculate Pi of this glutamic acid? We know the pK value. So, to calculate, we have to understand how its ionization, how its protonation and deprotonation occurs. Okay. So, again this is a pH scale, here 0 pH and here 14 pH, and let us mark all these 3 number on this pH scale. So, here suppose it is a point of 2.19, here suppose it is point of 4.25, and 9.67 will be somewhat over here. Okay. So, what will happen at this place, at the extreme low pH? At this place, all these 3 ionizable group will be in the protonated form. So, let us write down this COOH, it is in the protonated form. This COOH, it is also in this COOH format, and this amino group, it will be in this NH3 plus format. Why? Because it is extremely low pH, everything will be protonated. Now, you titrate this solution, you go on adding alkali, so pH will increase slowly. So, as you will cross this point, this 2.19, what will happen? This particular carboxyl group will start losing its protons. So, now this COOH group, which is this one, so it will be in the form of COO minus group. Then what about this carboxy group? Its pK is 4.25. So, this will be in the form of COOH, okay, and this amino group, it will be in the protonated form, so NH3 plus. So, here out of this 2 carboxy group, this one will get deprotonated and this one will remain protonated, so COOH format, and this NH3 plus will be also in the protonated form. So, this is the case. Okay. So, this level is crossed. Now, you go on adding more and more alkali to this solution. What will happen? pH will increase. So, now as you cross this point 4.25, what will happen? Even this carboxy group will start losing its proton. So, what will happen? This is already deprotonated. Okay. So, first this group, it is already deprotonated. So, COO minus. What about this group? It will now start losing its proton. So, we will also write it into deprotonated form. What about this amino group? It will be in the protonated form. Why? Because its pK is higher. Now, you go on adding more and more alkali, so pH will increase. So, once it will cross this mark, this 9.67 mark, what will happen? Even this amino group will start losing its proton. So, what will happen? Both carboxyl group are already deprotonated. So, both are deprotonated, and what about this amino group? It will also be deprotonated. So, NH2 form will be there. Now, let us calculate what is the net charge. So, here 0, 0 and plus 1. So, net charge is plus 1. Here minus 1, then for this carboxy group 0 and then plus 1. So, net charge is 0. Okay, this is important. So, I will highlight it. Okay. Here minus 1, here this minus 1 and this plus 1. So, we have net charge as a minus 1. Here minus 1 and 0. So, net charge is minus 2. So, now as you can see at this place between this mark and this mark, we are observing Zwitter ion, right. So, Zwitter ion is seen between this pK value and this pK value. So, to calculate the pK value of this glutamate, we have to average out this 2.19 and 4.25. Okay. There is no role of 9.67 in calculating the pK value of the glutamate, and by this it must be clear that why this is not important in the counting of pK value of the glutamate. Okay. So, to average out, so the Pi of glutamate is going to be 2.19 plus 4.25 divided by 2. So, 6.44 divided by 2 and the answer will be 3.22. So, by this you can calculate the Pi of glutamate value. So, now let us take up one more example of the lysine. Okay. And if you are confident enough and you think that you can calculate the Pi value of the lysine, please pause this video right now and try to calculate, and then come back to this video and continue watching it and see if your answer and logic is matching with this one or not. Okay. So, I hope your answer is correct, and let us try to calculate the Pi value, that is isoelectric pH of the lysine. So, first we must know the structure of lysine. We have central carbon. On one side we have carboxyl group, another side we have amino group, that is NH3 plus. On one side we have hydrogen, and fourth side there is a side chain R. Now, in this case side chain R is the 4 times this CH2. So, we will simply write CH24, and then there is a amino group once again. Okay. The second requirement is that we have to know the pK value of all the ionizable group. So, here the pK value of this COOH is the 2.18. pK value of this amino group, of the side chain amino group, is the 10.53, and the pK value of this amino group, this alpha amino group, it is the 8.95. Okay. So, now we have to calculate the Pi or the isoelectric pH of the lysine. So, for that again I will draw the pH scale. Remember, if you want to perfectly calculate the Pi value, this pH scale you have to draw it. Okay. So, here 0 pH, here 14 pH, and we have to mark all these 3 number on this pH scale. So, this is suppose 2.18, then second one is this 8.95, it will somewhere over here 8.95, and this 10.53 will be somewhere over here 10.53. Now, at this place what will be the scenario? this COOH and both amino group will be in the protonated form. So, first this COOH that is in the protonated form, this carboxy group that will also be in the protonated form. So, NH3 plus, this amino group will also be in the protonated form. So, NH3 plus. Now, you go on increasing the pH of the solution. As you cross this mark, what will happen? This 2.18, that is the pK of COOH. So, this carboxy group will undergo deprotonation. So, we have carboxy group as a COO minus, right? What about this both amino group? This amino group will be in the protonated form, right? So, NH3 plus, and this amino group will also be protonated form. So, it is also NH3 plus. Now, you increase more and more pH, and at one point you will cross this 8.95 mark. At that place, what will occur? This carboxy group had already lost its protonated, so no change in that. So, COO minus. Now, 8.95 is the pK of this alpha amino group, right? So, now this amino group will get under deprotonation. So, now it will be in the NH2 form. What about this NH3 plus? It will still in the protonated form. So, it will be NH3 plus. Okay. So, this type of ionization will be seen at this point. Now, you add more and more alkali to the solution. So, ultimately you cross this pH 10.53. So, at this place what will happen? Even this amino group will undergo deprotonation. So, all the groups will be deprotonated. So, COO minus, that is for this group. For this group also it is NH2, and for this group also it is NH2, right. So, lastly this group is undergoing deprotonation. Why? Because its pK is highest. So, now let us calculate the net charge. Here 0 plus 1 plus 1. So, net charge is plus 2. Here minus 1 plus 1 plus 1. So, net charge is plus 1. Here minus 1, 0 and plus 1. So, net charge is 0, which is important, right. So, here we can see here minus 1, 0 and 0. So, net charge is minus 1. So, Zwitterion is observed at this place. So, which two numbers we have to average out? This 8.95 and 10.53, because exactly at midpoint maximum Zwitterion will be seen. So, Pi of this lysine is the 8.95 plus 10.53 divided by 2. So, this summation makes 19.48 divided by 2, and so the answer will be 9.74. This is the isoelectric pH of this lysine. So, this was all about the amphoteric nature of amino acid, Zwitterion, isoelectric pH, and meanwhile we had also learned that how to calculate the isoelectric pH of particular amino acid. You can try to calculate the isoelectric pH of the aspartic acid and arginine and histidine, and please write down your answers in the comment section below. And yes, of course, if you have any query or confusion, please write it down in the comment section below. Thank you.